finish that last problem so you can see it. I got it all worked out, so, but then I'm going to give you the number 24, and you guys are going to work on that in class, and I'm going to answer questions along the way. And I might even give you some parts of the solution. Okay, we're recording, and we're here. I better share the screen. And Tim, thank you for recording the other day. That was a lifesaver. Yes.
No problem.
No problem. Trust me, it was more of a lifesaver for me than anyone else.
Okay, so we finished D right up in here someplace. Where the hell is it? Okay, we finished here yesterday or Tuesday. Okay, so we had to get the information to get it into the torques and the moments to come up with everything, and we had to go find SAE 1170, and I wanted to give you some details on what that was about. I don't know why I wrote CD in there. 140, say steel. So if you look up SAE 1170, the ultimate strength 69 KSI. The yield strength is 57 KSI, and I'm going to boggle your minds here for a little bit, but just so you know why we picked 1170, so there's 28% by weight carbon in this, 40% max of silicon, 1.48% magnesium, 0.4% is chromium, and then there's a 0.1 of molybdenum, all right, and then a 0.4 of nickel. So really it's that one and that one, the nickel and chromium, that make this a nice finish, okay? Molybdenum, this is added to make it machinable. Okay. And then magnesium is just another metal, and it makes it more lightweight. Okay.
Just 1 second.
No problem. But the 28% carbon is what's really in there. So without the silicon, the magnesium, the chromium, the molybdenum, and the nickel, this would have been 1028 steel, which is a low carbon steel. Okay. But we add this other stuff in here to make this a little better. So that's kind of where we're at. And I think this thing said someplace, and I don't think I wrote it down here, but I think in the back of the problem it said cold drawn. Okay, so that's going to give you the kind of surface finishing. Everybody good on that?
Yeah.
Okay. So the next bit is to go find your endurance stress. All right. And we got to find our size factor, and we got to find the reliability. Okay, so we go to this chart here. We take 69, and we draw a line up until we find the one that's machined or cold drawn. Okay, and we go left from there, and it gives us about 26 KSI. Nobody can argue with you whether if you picked this right or wrong, unless you picked it completely wrong. Like, picked 40,000 for it, wasn't even on one of the lines. Okay, you're interpreting a really fine detail out of a chart here, so, or out of a figure, so you can't really do too much with that. So 26 KSI is going to be the SN value. All right, that's the metric one that goes with it. Reliability is easy. Pick 0.81. All right. Unless they got some other reason they want you to do something with a different reliability value. All right, the size factor. Start at the diameter that was roughly given, I think was 3 inches, and run up till you hit the curve, hang a left-hand turn towards the CS size factor line, and it should be something like 0.75 is what I drew here. The book said it was 0.78, so you're really not going to argue too much with me. I bet it's more about where I put my line on there than where it wasn't. Okay, so we're going to play with 0.78, and then you can check to see if you are in the right place for your size factor. Okay, so we 2 inch to 10 inches for the D. We should be someplace between 0.85 to 0.02125 times the diameter, and that'll give you that number there if you really wanted to go back and check to see exactly what your CS factor is. But I'd go with the 0.78. Okay. Then we take all that and we put it into the modification of the endurance stress. And yeah, so 28 KSI times the 0.78 for the size factor, 0.81 times the reliability gives us 16.42 KSI, and we are definitely under the 26, so the 3-inch diameter should be okay. We go down and check for actual size here, and we plug all the numbers in here. And I don't know why I didn't write down the whole equation there, but probably should go back the last lecture anyways and see what that whole set of variables were. But 32 over pi was the section modulus. 3 is the factor of safety here, so that's your factor of safety. Factor of safety times your force in the vertical, or this one's torque, this one's your force, 3-dimensional force on that shaft, divided by the values for it. Okay, so 16.42 times 10 to the third, that's our SN prime. And then when you go over here, we're looking for the shear, or the tau stress, and 5700 or 57,000 was the yield strength. Okay, plug all that in, we get a number of 2.83. That works. Okay, we're under our 3-inch size, our stresses are good. The real trick would be choosing up to the next largest size. Okay, now I did one just to show you what if the numbers were different here in your size factor and playing this out. So if I did this and I picked 0.85 for the size factor itself, I'd get 17.9 KSI. Plug all that in there and we get a 3.7-inch diameter shaft in order to make that one work. Okay, so we had 26 KSI, but we modified it to reduce it, but then we're still not playing nicely with the sizes. That makes sense? Mike's nodding at me, so I'm going to assume the rest of you probably are. And when you get all done, it's too big, so we got to go back. And the last step to this, because we got a ring groove, and I didn't say this the other day, but it's in the reading, modify the ring groove by 6%. So you want to make it larger by 6%. So the D you got of 2.83 times 1.06 will give you a 3.0006 inches. Just turns out really haphazardly that 3 was what we were planning on, 3 is what we got. Okay. It'd been nice that it turned out like 3.92 or something like that, and then you just round up to the even number of 3. And trust me, there wouldn't be, I would never send a design up to the shop that says, I need a shaft that's 3.0006 inches. That's 6/10,000ths of an inch of precision. Never. At that point, 3.00. And then I'm going to look for plus or minus on the tolerances for the shafts and the bearings. Okay. Beyond that, I wouldn't get that carried away.
Why would you even need something like that?
There are parts that you do want that precise, but not in this world, not here. And if I was putting something in space, yeah, I probably don't want it to mess up. But no, and actually asking somebody to measure that accurately, they make devices that will measure that accurately, but most machine shops don't own one. So it's kind of stupid to ask for. Guys good there?
Yeah. Yeah.
Okay, that was James. How about the rest of you?
Yeah, more or less, I guess.
So more or less where or not?
It's just kind of like the whole process. Varying from problem to
Okay,
problem.
so you're going to get to another one here, and we're all going to kind of walk line by line down through it. Hopefully.
That's perfect. I
Hopefully.
started, but I definitely got stuck.
Okay. All right, so that takes us to this one. All right, so we got this shaft. We got bearing at A. We got set of pulleys at B. We got gears at B, right? Yeah, spur gear. And then we got a pulley at C. We got a pulley at D. We got a pulley at E. And we got a bearing out there. So literally we got a big shaft that when this gets all done, it could do this kind of thing. There's my bearings. Okay. And that's kind of the deflection you're going to see on this thing. Okay. All right. Problem. A part in a special machine to reclaim scrap aluminum cans. The gear at B delivers 5 horsepower to the chopper that cuts the cans into small pieces. The V-belt sheave delivers 3 horsepower to a blower that draws air through the chopper. A V-belt sheave E delivers 3 horsepower to a conveyor that raises the shredded aluminum to an elevated hopper. The shaft rotates at 480 RPMs. All power comes into the shaft through the chain sprocket at C. What was C looking like? C was, where's that picture? All right, so C is a sprocket. Cool. I misread that. I thought that was a pulley. SAE 1137. So it's in that same as the last problem. It's going to have some molybdenum and manganese, chromium, and nickel in it. And we are looking for an OQT 1300 steel for the shaft. I want to go look that up. I didn't even go pay attention to that stuff. Cool. I think this is quenched steel at 1300 degrees. But I want to go confirm that. So the elements at B, C, and E, B, C, D, and E are held in position with retainer rings and keys in the profile seats. So very similar to that last problem. Okay. All right. So where'd you start?
With the 480. The 480.
With the 480. Okay. So we got a shaft that goes at 480. So looking for the torques, right?
Yeah, torque next. Yeah, torque next, right?
Yep. So our N is,
B and D. Can you only do B and D, or?
You can do B and C. Well, actually, you can do all of them to get your torques.
Okay.
Yeah, for C, wouldn't we just use the horsepower of all the other ones combined since it's the only input?
Right. So torque at B, actually the other thing would probably be is a decent free body diagram of the horsepower here. So this one is at B, we're delivering B, 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 B. 5 horsepower. All right. And D delivers 3. All right. And then E takes 3 too. Did I miss one? D is 3.
Is that same size? Same
E
size.
is 3. Yeah, they're both 4-inch diameter sheaves. And C delivers. Okay, so I'm going to go C that way. So actually, minus, 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 plus. So that's 11 horsepower. They didn't tell us that, did they? No.
Nope, that's not something they gave us, but it's something.
But that is how you get that. You just add them all up. So whatever goes in must come out. The whole thing of continuity again. Okay. So the torque at B is the conversion to get the horsepower divided by the RPMs. So just to make sure you guys understand this, but horsepower is torque times the RPM divided by 6,300. Okay, and the 63,000 is a conversion factor. Okay, so that's why they're always putting this in this way.
The 63,000 have any units for the conversion? What
Oh
the
yeah,
units be?
horsepowers per RPM leads into the pounds per inch. So it gets ugly here. No, wait a minute. Did I just do that wrong? No. Yeah. So yeah. So we got inch pounds. We got RPMs, and we're going to get this will be 6,300 inch pounds RPM divided by horsepower, something like that. How's that? Still not quite exactly right, but that'll suffice.
Yeah, just
We should. It should be something like this, James.
So
Inches, revolutions per minute, divided by 6,300 inch pounds, revolutions, minutes, and horsepower.
That's fantastic.
Something like that. You can Google that one. It'll show up someplace. So anyways, our horsepower here is 5. I'm not going to worry about the negative. What I was worried about with the negatives and the positive here, I was trying to remember that the 11 is my input power, and the 5, the 3, and the 3 are the outputs. Okay, so we're only going to play with that just to make sure that we add it up to 11 here. So 5 horsepower divided by 480 RPMs. Okay, and that's that one. Okay, and I'll give you this one as 60 or 656. Okay. All right, so D and E are the same diameters, so we can find the torque at those two guys, torque at D and the torque at E. Anybody got a solution for that one?
I had 393 and 0.75 for both.
So I'd round that to 394. Don't fight with the decimals.
Cool.
It's kind of like, you remember the conversations in the past where we'd go, it's 35,759 pounds per square inch. And we'd say 3 significant figures. So you'd round it up to 37,700 pounds per square inch, and we're good. Remember kind of doing that stuff?
Yeah.
So hanging all those decimals out there isn't going to make your life any better or worse. Just gives you more numbers to play with. All right, so the sprocket at C. So at TC, what do you get?
I got 1,444.
Cool. Make sense? Okay.
That's the output one,
Yep.
right?
Well, that's the input.
Yes. Yeah, sorry. That's what I meant.
Which should make more sense when you see all this, and going back up here to my little goofy ass diagram, what ones were powered which way. So input was the 11, and then 5, 3, and 3 were my outputs. Okay. All right. Okay, here's the one thing that's new in this, and this is more for just FYI to make your life just a wee bit simpler. We didn't do this in strength of materials, but a torque distribution diagram. So really, we got 0, B, C, D, E. Okay, so it really goes up, over, down, over again, up, over, and back. Okay, let's do that. There's a tick mark there. That one's D. Let's get that one out of there. Move E closer to this side. Okay, and 656.
Okay, so this is how we figure out what point is going to basically be our breaking point with the torque, where we solve to the right and left of is C.
C. Let's see, what do we got? 656 and 3. Dun, 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 dun. And C was 1144, so 656 minus 1144, 788. Okay, and back up 394. So that should take us to 394, and then back to 0. Okay.
Did you get this 788?
16. Well, so this 788 became T at C was T of B minus the TC, which is kind of stupid nomenclature. I'm apologizing here. $1444, right? Yeah, 1444. Make sense? Okay. So again, any place where the transition crosses at 0, Just like when we find our maximum moments, those are those places. The interesting thing is we actually got 2 points. So I'm looking ahead at the moment diagrams. C is not going to be our most significant place, but it is something to be worried about for a little bit here. So turns out D is actually our most critical spot. So all right. So anyways, that just helps you get an image of what you just did up here, and probably worth it because I don't know about you, but I'm a visual learner. If I see something, I kind of remember what those shapes look like and what goes on. All right. So the next step. Find the force on the gear. Anybody do that one?
No, this is where I stopped.
Same.
Okay. So what's the equation I want to look at? Do you remember these two?
Is it the F1 step 2?
No, that's for pulleys.
Oh, yeah.
The gear is, so remember the gear is this thing. We got this fun stuff here and that fun stuff there. So we're looking for the radial and the tangent forces.
Right.
Okay. So basically WTB is T at B over the radius at B. And you guys can look the math up. I'll give you the numbers. 437 pounds. And that's FB of X. Okay. And then I did capital R again. I don't know why I do that every time. Of B.
My step sheet's not loading on Teams. What step is this on the sheet?
I have no idea. I've lost track.
I'm just trying to keep track of it on my paper as well.
I have this one as 7 in my notes.
Okay, that's what I thought.
I got my step sheet. I found it. Yeah, determine forces on the shaft, both radial and axially.
Okay. I was just confused because I think we probably skipped some steps that we don't need to write all out.
Right, you just have to identify. Like I didn't actually write. I mean, I wrote the RPMs down, but that's your first step.
Yeah.
All right, so WB tangent requires the tangent of 20 degrees. That was given to you in the figure. And that one turns out to be 159 pounds. And that's going to be FBY. And the other thing is I should put, make sure we get this right. This one's going in that direction for positive, and this one's going in that direction for positive.
And so I guess when I stopped here, it wasn't because I wasn't really sure what to do. It was more because I didn't really know where to go for the equations. Are they just going to be in that section of the chapter? Depending on what we're doing. This one's a spur gear, looking at the spur gear section, basically.
Yeah, so you got to go back to the stuff we've taught all through the semester long now. Yep. So gears is gears. That's where these two equations come from. Does that make sense to everybody?
Yeah, that makes sense. I'm just confused on like your numbers, where you got those from.
Oh, I don't know. I'm just taking them out of the solution at the moment. But
TB, like what would your TB and your RB
so TB was 656 and RB was 1.5.
The torque on that gear B and the radius of gear B.
Yep. So the radius on the spur gear, well, the pinion here, that's the small one on the shaft, That's 3 inches in diameter. That make sense, Matt?
Yeah, it does. I'm just trying to look at the picture and like swipe back and forth between the notes.
Yeah, it's kind of where, I hate to say this, I'm not sure how to do this electronically that way. Almost years ago when I had the book out, I always just had the book laying there and I could look back at the picture, and even though I had stuff on my sheets, I didn't have to go all the way back, so.
Right.
I get it. We just took our torque and then we just had the half.
Yeah,
the
take the torque and divide by the radius to figure out what the force is on the,
It's more or less the nomenclature messes me up. It's just like not all the switching around and stuff.
okay. All right, so that's the stuff on B. All right, now find your force on your sprocket. Sprocket, SP rocket. Spacely sprockets, we're here to say. Sorry. And that one's going down in that direction at 15 degrees. All right, and that's off your drawing up here. So that guy right there. Keep that in mind because we're going to have to convert that back here in a second. So, okay. And so F C of X is your next step, because we've got to take that three-dimensional force, take it two-dimensionally so we can put it on the shaft, so you figure out what the moments and shear diagrams are going to look like, and figure out the max moment, combine them back into a three-dimensional moment. It's all about decomposing things and then reassembling them. Okay, so those are the directions going down. So that's a negative, that's a negative. Everybody good up to that point?
Yeah, doing pretty good. Yeah, doing pretty good.
So what's left?
Yeah, I think so.
Okay, so we got the forces on sheaves.
I actually have a question.
Sure.
Why did we and out of this may just be because it's the equation. Why did we use tan for B, but we broke it up into components for C with the 15.
So
what's said in the picture?
This one is
20.
We are looking. Get out of there. So if I was to take these forces, the radial force acting on a gear and this one working this way, although let's do it in the right direction. So this there and this there, okay? So WTB here and WRB there. So if I want to know what that is here, actually I don't want to do that one, sorry. I want to do the, I do want to do that one. I want to do that one so that I know what the W is on that gear. So if I look at TB, it's the torque here. I need a better picture. Hold on. Let me draw it like this. There's my gear tooth. We're going around. Okay, so one gear tooth. One hell of a gear. But as I strike that, I'm actually doing the force in this direction, W, but I know it's the tangential force that I'm playing with. And the tangential force comes from the torque at B and the radius from here to there. So the one that I know, Matt, is WTB is TB over RB. That makes sense?
Yeah. Yeah.
Okay, and then in order to find the vertical force of that, I got to take really what is W and do the tangent of it.
Got it. Okay.
Okay, so we are the sheaves. Mikey, this is your equation. I'm gonna name it the Mikey equation.
Oh boy.
Somebody probably already has dibs on it, but so if you look at these, let me go back up here and get this picture. So D is actually working straight up. E is going to be off at a 30-degree angle. But let's do this way. So what I'm looking for is I got this and this, F1, F2, and I'm really looking for this, okay? So in order to get that, I gotta know what's going on with the two forces on each of those belts, okay? So again, it's still the TD. So I literally have this going this way. I got a torque, and I got some radius R, and that is why I'm doing F1 minus F2 is equal to T over R. Make sense?
Yeah.
Okay.
And that's specific to the sheaves,
Yep,
right?
because I got two belts. I hate to say two belts. I always think of it as two belts, but I got one belt that's under great tension. I got one belt that's not under great tension, but it's still pulling on the shaft. Okay? So that's why it's F1 minus F2. F1 is usually your drive. F2 is one going the other way.
Okay, and so then we just end up using that to find the total force.
Yeah. So FD here is what this is. F1 plus F2, which if we do this, someone figured out years ago that if you do this, all right, and you can get 1.5 times 197 pounds, you will get 296 pounds. So I relate it this way, which is maybe not the right way, but it always helped me think of it. F1 is 1 and F2 is 5.5. It's half of what F1 is. Not really, but it makes some common sense if you think of it that way. F2 is under slack. It's not pulling the same force. That makes sense? Corny dumbass way to try to remember it, but okay, everything on this one's going vertical, so this FD is really FDY is 296 pounds, and FD of X is 0. Okay? And that's going up. All right, now force on sheave E, FE is equal to FD, which is 296, because they're the same diameters and the same RPMs. Okay? But it's acting at some weird angle, which was what? Anybody remember what that angle was up there?
30?
Yeah,
30 degrees.
Yeah, 30 degrees.
Okay? So 30 degrees. In essence, we are going to get FE of X is FE times the cosine of 30 degrees, and we're going to get 296 cosine 30 degrees, and that's 256 pounds in that direction. And FE of Y will take you to 148 pounds going vertical. Okay? All right. So now you're down to we got to do horizontal, and we got to do vertical. Okay, so your free body diagram looks something like this. All right, so we got A, B, A, we got 4 there, B, we got 6, we got a force here, that's C, we go 6, we got D, whoops, we got a D, we got E, that is this, that's 4, 4, and we got an F out here. All right. Did I miss anything? Oh yeah. B's climbing upward. All right, so 437, 75, right? What's that number? 75. 256. Okay. And then you got to find your reactions. So basically a little footnote here, find reactions. AX and RFX. Okay? You guys can you do that part? A, B, C, D, E, F. And we are 4, 6, 6, 4, and 4. Okay? Find reactions AY. Okay. $363, and this one is $255, and this one's $430. No, 93, and this one is 231. Is that right? I think that's right. Good there? I'm going to let you guys draw the shear and bending moment diagrams, but I'm going to give you the answers so you can see what they look like. So you want to find that, which is going to be your max moment of D at X squared plus max moment at D of Y squared. And if you do this right, you should get 1613 pound-inches. Okay? And everything came with a ring on it, right? I'm pretty sure. Instead of a ring groove. So TD is 788 pound-inches at D to the left. With a KT value, because it's a ring groove at 3 for a retaining ring.
They also QAs as well.
They do what?
They all have QAs as well.
Okay,
I'm pretty sure.
Well, we'll deal with that one. What are we gonna deal with that one? Yeah. So KD is 2.0, right? No, 2.5 for keyways. What did I use in the last problem? Two for keys. Okay. So far, so good. You guys got to draw the bending moment diagrams, come up with some numbers. And then really, we're just down to this step. So SAE 1137 OQT 1300. It's got a S ultimate of 87 KSI. We get a SY equal to 60 KSI. And then your SN, you got to grade it off the table, should be 33 KSI. Okay. Then what you're doing is looking for S prime N is going to be SN times your CS and your CR. Okay. And remember, this CS right here is just an estimate. So if something goes wrong, you don't get the right size, go back and change your size factor. Make it bigger or smaller, which is why a spreadsheet would be really handy. Okay. From there, you're going down to D for D, and we're going to do 32 times the factor of safety divided by pi, square root of you know, it really sucks when that equation's not right there. Where did I put that puppy? KT M over SN prime. Okay, one little footnote here. Okay, so we want to go with the 3-0 for the ring. Okay, the key is going to affect it, but why don't I carry so much weight on the key? Remember what I did at the last problem here?
I unfortunately don't.
So remember, I multiplied the key times 6% to make it larger, or the shaft by 6% to make it larger.
Right.
So the key is a stress factor, but the ring groove itself is going to dominate. Okay. If I didn't have a ring groove, then go put the keyway in there, because that's the one that's going to dominate. All right. So that one's going to go to 3.0.
So essentially, you just use the higher KT value of what you have in the problem. Or what is it?
I'd say yes, but I want to make sure that what you're getting is not just choose the higher one. I want you to think about which one is going to help increase the size of things, make it bigger. Okay. So the ring groove, when I get all done, I got to multiply times 1.06. So I'm going to wind up with well, actually, I'll give you the answer here. So the answer to this one turns out to be 1.83 inches. But then I got to go DD modified. is going to be 1.06 times 1.83 inches. And we're going to get 1.94. So we're going to specify 2.0 inches. Okay? So if I do this and put in the KT value, this diameter is going to be smaller to start with. Okay? And I don't want to do that. I want to use the one that's going to give me the larger diameter to start with and then modify it.
Right.
Okay?
Makes sense. Makes sense.
Let's see, what's left in this problem? So when you're done there, go check your SC of, what do we use? Oh, I didn't tell you what we used. Anyways, go back and check that and see if, go check CS and recalculate. Diameter at D required. Okay. And you'll get something like 2.01, and using DD of approximately 2.0 inches is okay. And those are the steps to that solution. Cool?
Yeah, that was very helpful. Yeah, that was very helpful.
Okay.
Thank you.
You guys fill in the details and show it to me when you get back.
All right.
Okay.
Yeah, more or less just all the equations. Just to complete the problem. Just to complete the problem. It's just a lot.
There is a lot, and we're also pulling a lot out of other.
To remember where to look for certain spots and stuff, and where I'm supposed to pull off of certain whatever charts and such. And
okay, we'll give that a shot and let's see how it goes. You want another one to practice?
Actually, yes, that would be awesome. That would be awesome.
Then I'll get back up to the office. I'll copy 25 in, and you can play with that one. Same idea all the way down through.
Cool. Thank you.
Okay.
Cool. Thank you.
Cool. All right. You all have a very good holiday. Get some rest. Don't do anything stupid, and try not to bring any COVID back with you. How's that? See y'all later.
got it. Have a good holiday. Have a good holiday.
Sound.
So we don't have any homework or anything, just like figure this out and
Well, I'm going to give you 25. You guys can do that one too.
okay.
So yeah, you do have homework, but
Well,
it should just follow these same exact steps.
I didn't know if it was.
I don't even know if 25, because I don't have the real picture. I just got the shear bending moment diagram. It's got a gear, it's got a sprocket, and it's got shafts. So it's got a, oh, that one's easy. One gear, one sprocket, and 2 bearings. Damn.
I just figured I'd ask, you know?
Yeah, I want to do something. You guys got to get caught up here. So, is any of this stuff recyclable, like, you know? Cool.
Yeah. So, I'm not sure if it's recyclable, this stuff, is no specific thing, but like you can, oh yeah, recyclable.
Oh, this stuff is not the ABS stuff, the regular PLA. It's like,
Yeah. So if you mean like recyclable as in like you can bounce it down again,
nah, like that, just go with some plastic cycle process.
so with this, with the actual resin, it's toxic, so it has to go to like a specific treatment plant. So there's a waste facility in Potsdam that has to call it and but they said that they take sub 3D printer stuff, so it's fully cured, doesn't matter. The stuff in there isn't fully cured, but it's like 98% cured or something like that.
Yeah, so just say pure instead of having
So this is just a heavy UV light, but like if you want to, you just put it out in the sun for 2 days.
So the real trick is any material left over just gets used.
Yeah.
Turn into something.
Well, any material left over either stays in this, like,
Right, as long as it covers down and it's not gonna be exposed.
right, it's not gonna evaporate or anything. In theory, the cover protects it from UV, which there was some stuff sitting in here that said left. So like, and it, I break it and it still looks fine. But that's probably mostly gone because we've printed a decent amount of stuff of it. But the thing with this is, they use these cartridges, which are proprietary, and they got a little computer chip in it. And it says like, oh, you printed, I don't know, 70 milliliters of stuff, it's empty. And then it'll yell at you, hey, this is empty. So you gotta buy a new one. Versus like, personally, I'm a cheapskate. I wanna play with it, I wanna see if I can make it just say, okay, go, So I wanted to see like, can I fill this up with different recipes? So I can buy stuff like this for 30 to 50 bucks. To buy one of those, it's 150. For school, whatever, it doesn't matter. But I'm curious,
Yeah, because every little bit will save some money and stuff.
Yep.
And all we're doing is soaking it out of your tuition.